Okay, so one comment I wanted to make before we begin also is that the first installation of our lecture notes will be posted today. So there are details for everything, which, and it's carefully written. And the only thing that I have to do is write up what we talk about today, and then it'll be there. And there are some things that got sort of shoved into the lecture notes, which I think might clarify the average type stuff, if that is in any way unclear. So, be on the lookout for that. And I'll try to post at least weekly, but perhaps more, depending on how much progress I make in writing them. Okay, so the course up to now has been concerned with finding indiscernible sequences, and today the goal is to use them. And so the plan is to prove two theorems, which I think are both rather beautiful theorems about stable theories and about the meaning of stability. And both of them are fairly straightforward once you have indiscernible sequences sort of in your toolbox. And neither of them is particularly deep, but both are very important. And so I think it will serve as a kind of illustration of why indiscernible sequences are useful in combinatorial arguments in model theory. Now, the place to begin is with the definition. So I'm going to define the order property. And I think like if you've ever gone to a model theory research talk, like a seminar or something, you've probably heard the definition before. So hopefully this is a familiar thing. So we say that the formula phi x y has the order property.
Nick, could you share the screen?
I didn't. My goodness. Thank you. Yeah, that's important. Oh, whoops. Okay. Thank you. Yeah, that's important. Also, you were going to, I was supposed to mirror my video, and let me see if I can do that. I don't see how to do it. I'll have to play around with it, but I promised you that I would do it, so I will. Anyway, so everyone can see this now. Phi has the order property. If there are ai, bi, I less than omega, such that you satisfy phi ai bj if and only if I is less than or equal to j. So you have some collection of tuples, and the order on their indices is somehow coded by the behavior of this formula. And just a remark, T is stable if no formula has the order property modulo T. Okay, so the best place to start with this is just with an example. And the easiest example that you can think of is, of course, anything with an order around. So let's do, say, the rational numbers. So our first example will just be, we take the rational numbers with less than, and our sequence can be ai is I, which is, of course, a rational number for all I in the natural numbers. And then our formula can just be x, or sorry, bi can also be ai. So x is less than or equal to y, can be our phi. Then, of course, it is true that we have phi ai bj if and only if ai is less than or equal to bj by definition of the formula, and that happens if and only if I is less than or equal to j by definition of our sequence. So this is almost tautological. If you have an order around, then you have the order property. But interestingly enough, there are lots of examples where you have the order property and you have nothing like an order around. And so the definition, I mean, it picks up on a form of order which is not necessarily explicit. You don't necessarily have an order that's interpretable or definable in any way. And a good example to have in mind for this is something like the random graph. So this is example 2, and we will have GR is the random graph. So I imagine that most of you have thought about the random graph at some moment before, but if you haven't, what the random graph axioms say is if V1 through V2n are vertices, pairwise distinct, then there exists some vertex W. Oh, sorry, it's being wonky. There's a vertex W such that for every I from 1 to n, I connect to those VIs, and I don't connect for every vertex indexed by n plus 1 to 2n, I don't connect to the rest. So you have some graph, G, and whenever I take two finite sets, I've got some vertices here and some vertices here, I can find a vertex which connects to all of these and to none of these. And okay, that's a useful kind of object to think about. This graph is very simple to understand. It's all if not categorical. It's a first-aid limit of all finite graphs. But one thing that you can check sort of by hand is that there are no orders definable inside this structure. You know, anytime you have a relation that acts like an order on something, you can check that it's not going to be transitive. And so there's simply no orders in sight. And this is something that you can give yourself as an exercise. Prove that there's no interpretable partial order in the structure. But nonetheless, it does have the order property. And how do you see that? Well, in G, you can find AI, BI, let me say it this way, pairwise distinct. As I ranges over the natural numbers that look like a half graph. So let's say here we have AI and BI. Or actually, let's give these particular indices. So this is like A0, B0, A1, B1, A2, B2, A3, B3. And our rule will be that you have a connection from AI to Bj if and only if I is less than or equal to j. So graphically, this looks like this. Not a very good drawing, but okay, something like that. Okay, so on these tuples, you act like an order because the formula Rxy, only holds if the indices are in the right order. But the tuples on which you act like an order is not definable. And for this reason, you have something that looks like a very random structure which has no order in sight, but sitting inside on some tuples, you can find an order. So it's important to remember that the order is not definable. So it's going to be a different property. All right, so
Nick, what do you mean by has the order property modulo t?
Yeah, so what I just mean is that some formula has the order property where the tuples that I'm talking about are found in a model of T. When I mean modulo T, I mean like this formula, which exists in the language L, has the order property when interpreted in models of T. Because of course, like if I throw a binary relation into the language, there can be structures in which I interpret that as an equivalence relation, in which case it doesn't define an order. And then there can be structures where I interpret it as a linear order, and then it does. So what I mean is like fixing the theory, the formula has the order property, because that obviously depends on the theory.
And it doesn't depend on the model of T that we choose?
Well, the way I've defined it, where I have infinitely many tuples, it certainly does depend on the model, because maybe you need some amount of saturation to get the infinite quantity. But this property is equivalent to saying that for every n, I can find tuples AI, BI up to n, such that AI, BJ holds if and only if I is less than or equal to j.
Mhm.
And that property, you can write a sentence in the theory that says there exists, x1 through xn, y1 through yn with this configuration.
Mhm.
And that will just be in the theory if the theory is complete. So the finite approximations will occur in every model of the theory, but in order to find an infinite configuration, perhaps you need a little bit of saturation. So when I say it exists without specifying the model, I always mean the monster model, but you're exactly right. If I was just talking about arbitrary models, to have the order property means that there is some model where this configuration is found, and it's equivalent to saying it's in a sufficiently saturated model. But it might be possible to find particular models where it doesn't appear. And in fact, this distinction is important just as a sort of interesting bit of trivia. So you can have relations which are somehow stable in a model, which are not themselves stable. And sometimes this regime is interesting. Like Gabe Conant, for example, has some papers where he studies stability in a group, which doesn't look at the elementary class, it just looks at the model itself. So sometimes this distinction is important. So it's a good point.
Thank you.
All right, cool. Are there any other questions? Nope. Okay, so what I'd like to do now is I want to define a different kind of indiscernible object. So before we had an indiscernible sequence, now we're going to define an indiscernible set. So we say AI, I in I is an indiscernible set over A if whenever I0 through I n minus 1 in I are pairwise distinct, and J0 through J n minus 1 in I are pairwise distinct. When I look at the tuple indexed by the I0s, and the tuple indexed by the J0s, they have the same type. So what's different here than the definition we had in the very first lecture of the notion of an indiscernible sequence? Well, in the notion of an indiscernible sequence, we say if I have an increasing in tuple, I0 through In minus 1, and another increasing in tuple, J0 through Jn minus 1, those have the same type. Now here we have not insisted that these tuples are increasing. So what is different here is that the order does not appear. So I can scramble two tuples. Maybe I take one tuple and then I represent it in a different way by scrambling it, then it should still have the same type. So let's give an example and a non-example. So an example, we had this example on day 1, which is the theory of an equivalent solution with infinite classes. So an equivalent solution with infinitely many classes, all infinite. Now I can take a sequence inside this, which just consists of one element in any class. Now, if I take a pair here, let's say I list this one first. So this is going to be I0 and I1. What does the type of this pair say? It says they're not equivalent, and it doesn't say anything else. That determines the type because you can check by quantifier elimination. That's all it says. Now, if I take a different pair, let's say this one, and let's say I index the one that appears last first. So I write like J0 and J1. What does the type of the things indexed by these two say? It says they're not equivalent. The order doesn't matter. So these two things have the same type. And it doesn't matter whether I picked the one that came first or the one that came second first, right? So this is an indiscernible set. Now let's do a non-example. So let's just look at the theory of dense linear order, looking at the rational numbers. Now, sitting inside of the rational numbers, I can just take the natural numbers themselves. So I've got 0, 1, 2, 3, 4, 5. And the natural numbers sitting inside of the rational numbers are an indiscernible sequence. Because if I take, again, you know that this structure has quantifier elimination. So if I take, say, a pair here, I0 and I1, what does its type say? It just says the thing indexed by I0 is less than the thing indexed by I1. And that's all it can say. And if I take any two tuples from the sequence of natural numbers, if I list the lesser one first and then the greater one second, the type will say the first one is smaller than the second one, and that's it. So this is an indiscernible sequence. But suppose I take a different pair and I put J0 on top and J1 on bottom. So it looks like this. Now what does the type say? It says that the first one is greater than the second one because I list J0 first. So here we see, so recall I'm defining a sequence now so that AI equals I for all I and omega. I see that with this choice, we have that I0, I1 does not have the same type over the empty set as J0, J1. So this is an indiscernible sequence, but not an indiscernible set. Of course, being an indiscernible set implies being an indiscernible sequence, but the converse, as we've just shown, is false. So those of you that know some model theory might instantly recognize that there's a kind of fundamental difference in the complexity of these two theories. If you know stability, then you'll recognize that the first example is a stable theory. The theory of an equivalence relation is as stable as it gets. It's omega stable, Morley rank 2. And then the second example is the canonical example of an unstable theory. You have the order property because you have the order around. And so in the first example, we saw that the indiscernible sequence we picked was an indiscernible set. And in the second example, we could very easily find an indiscernible sequence, which was not an indiscernible set. And what Shelah has proved is that this distinction is characteristic of the difference between stable and unstable. So this is the first theorem that I want to talk about today. So theorem, this is Shelah. This is in the book classification theory, if you get interested, although it'll also be in the lecture. Okay, so the following are equivalent. So one is no formula has the order property modulo T. So recall we're working in some theory T. And two, so this is another way of saying T is stable. And two, every indiscernible sequence in a model of T is an indiscernible set. Okay, so, and this makes sense because what is the difference between an indiscernible sequence and an indiscernible set? The difference is that an indiscernible sequence keeps track of the order and an indiscernible set forgets it. So if your theory codes orders, then perhaps the indexing set's order matters. But if your theory doesn't know anything about the order, then you can't expect it to make this distinction. And so these two notions should collapse. And that's more or less how the proof goes. So let's prove this. So I'll start by proving 2 implies 1. But I'll really prove the constant positive, so not 1 implies not 2. So what we're going to do is we're going to assume that we do have a formula with the order property, and then we'll cook up an indiscernible sequence, which is not an indiscernible set. So assume phi xy has the order property witnessed by the sequence I, which is Ci I less than omega, which is the pair Ai Bi I less than omega. So I'm just using Ci to name this pair, and recall that our condition on witnessing the order property means that i.e. phi Ai Bj holds if and only if I is less than or equal to j. Okay. So great. Now, what we'll do is we'll take j, and I don't know, let's call these elements di, I less than omega, which will be ei fi. It's also a sequence of pairs. An indiscernible sequence which realizes the EM type of I over the empty set. So I won't write it. All right, and we have 2 proofs now that this is a possible thing to do. So we start just with some sequence, which witnesses the order property. And from that, we can find an indiscernible sequence that closely resembles it. Now, because for all I less than or equal to j, we have that phi ai bj holds, and for all I less than j, we have not phi a j b I. What we can conclude is that this is reflected in the behavior of our indiscernible sequence. So we have phi, what did I call them? EIF FI. So we have EIF J holds if and only if I is less than or equal to J. Okay. Why? Well, when does a formula go into the EM type of your sequence? It happens to go into the EM type whenever, no matter which increasing pair I take, some formula is true. The EM type just encodes the information that's true no matter where I look in the sequence. And because this relationship was true for any pair I and j, I know that it has to be true also for the indiscernible sequence that realizes the EM type. Okay, so in particular, is less than j, we can define, or actually let's be even more concrete, because now we're indiscernible, so we can fix our attention to any pair of indices we like. So what we'll do is we'll let I0 equals 0 and I1 equal 1. Why not? And we will let J0 equal 1 and J1 equal 0. So we're going to take this pair and swap them. Then we have phi of E I0 F J0 and not phi, sorry, I mean I1. that's poor form, I1, and not phi E J0 E F J1. Sorry, I'm all over the place today. F J1. So now I'm being a bit pedantic, but if we define C of x0, y0, x1, y1 to be the formula, let's say, phi of x0, y1, we have C of di0, di1, and not C dj0, j1. This is just a translation from what I said before, reflecting that now we're looking at the tuples in the sequence j. And this implies that j, which as we recall was the sequence of di's, is not an indiscernible set. Because I found two tuples, both of which consist of two pairwise distinct elements. And if I plug one of those tuples into the formula, I get something true. And if I plug the other tuple, I get something false. And that means it can't be an indiscernible set. So that concludes this direction. And this shows you that if you have the order property, then there's no way that every indiscernible sequence can be an indiscernible set. Because in particular, the formula that witnesses the order property will tell you how to distinguish the order on the tuples. Okay, so this is one direction, which is the easy direction. And now we want to take an indiscernible sequence, which is not an indiscernible set, and we want to play games with it so that we can produce a formula that does not have, that does have the order property. So now we'll go the other direction. Is this argument clear? Okay, so now we're going to prove not 2 implies not 1. So assume I is an indiscernible sequence that is not an indiscernible set. Now, by the remarks that we made at the beginning, by compactness, we may assume I is equal to AI, I in Q. So we can assume that the order type of the index set is the rational numbers. And it's easy to see by compactness that if you have an indiscernible sequence of any infinite order type, then you can assume that it is indexed by any other infinite order type. So without loss of generality, we can just assume that the indiscernible sequence in question is indexed by the rational numbers. Great. Okay, then there are I0 through in minus 1, pairwise distinct, J0 through Jn minus 1, pairwise distinct in Q, such that for some formula, in the variables x0 through xn minus 1, we have phi ai0 through ai minus 1, and we also have not phi a j0 through a jn minus 1. If for every formula and for every pair of increasing n-tuples, one is satisfied if only the other is satisfied, then that means that it is an indiscernible set. So if it's not an indiscernible set, then that will be witnessed by distinguishing the behavior of two tuples on some formula. And phi is going to be the name we give to that formula. Okay, so now let's just draw a picture very quickly. So here we've got our sequence indexed by Q, and sitting inside of Q, I've got, some natural numbers, and we have our two tuples. Let's suppose they both have size 3. So here's like I0, I1, I2, and then we have, I don't know, J0, J1, J2, something like this. Now, notice that these guys, which I wrote in order, right? I wrote I0, then I1, then I2. Anything that's true of the tuple indexed by this triple will also be true for 0, 1, and 2. Why? Because it's an indiscernible sequence. So of course, if I preserve the order, I can slide them. And likewise, if I slid J2 to 0, J0 to 1, and J1 to 2, like this, then the behavior would also be the same, right? Because it's an indiscernible sequence. If I slide without switching the order in which I write the tuples along an indiscernible sequence, the truth values don't change. So without loss of generality, I can assume that the set I0 through In minus 1 is equal to J0 through Jn minus 1, which is equal to 0 through n minus 1, like the natural numbers sitting inside the rational numbers. Why? Well, because I can just change this n tuple by sliding it and rearrange it so that it agrees with 0 through n minus 1. So I've got two n tuples. They're going to be in different order, but I can assume that they're both the same set using the indiscernibility of J, or I, sorry, by the indiscernibility of J. Okay, now additionally, without loss of generality, I can assume that one of them is just 0, that I0 equals 0, I1 equals 1, dot, 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 I n minus 1 equals n minus 1. Now, this is a little bit less clear, but let's think about why. So the tuple I0 through In minus 1 and J0 through Jn minus 1, they can't both agree with the tuple 0 through n minus 1, right? Like, if I can look at this formula, which is like A0 through An minus 1, either this is going to be true or it's false. Now, one of those possibilities will either agree with I0 through In minus 1, or it will agree with J0 through Jn minus 1. So let's assume that it agrees with the I0s. So then I could just replace the I0s with this thing, and then I'm still in the same situation, right? Now the alternative is that I agree with the J0s, but then I can interchange the role of I0 and J0 and replace phi with not phi. So without loss of generality, I can assume that one of the tuples that I picked is just the numbers 0 through n minus 1. Okay, so now we've reduced to the following situation. I've got a single permutation of 0 through n minus 1, which switches 0 through n minus 1 from being true to false. So now we're going to do something kind of tricky. So now we will recursively define J0 superscript L through Jn minus 1 superscript L such that a few conditions are going to be satisfied. So the first one is just that when the superscript is 0, I've done nothing. So J superscript 0 I is equal to J sub I for all I less than n. And 2 is if it's not the case that J0L is less than Jn minus 1 superscript L. So if it's not the case that they're all in order, then for K, let's call it K of L, it depends on L, least such that J IL equals KL J I prime L equals KL plus 1, and IL is less than, sorry, I prime L is less than IL, we let sigma be the permutation that swaps IL and let me make sure that this is what I want to do. Yeah, this is right. So we swap IL and I prime L and define JL plus 1 I to be J of L sigma of I for all I less than N. Now this is super confusing. So let me define it explicitly, and then we'll give some examples. So explicitly what I mean is that J of L plus 1 of I do nothing if I haven't seen some of these bad indices. Now, if I'm equal to I of L, then I swap. So then I give you K of L plus 1. And if I'm equal to I prime of L, then I swap. So basically, the idea is I have a way of enumerating the set 1 through n. And I look at the first place where I take a number and that number appears oh no. Sorry, I did it back. No, I did it right. I wrote it right. Yeah, I look at the first place where the number plus 1 occurs before the number, meaning it's out of order, right? So there has to be some place where a number plus 1 occurs before the number, and then I swap them. So let's see an example. So let's look at the following example. So suppose I have 3, 2, 1. So what's the first place where a number shows up after that number plus 1? That's 2, right? So here I see that 2 shows up after 3. The number plus 1 shows up before the number. And then I swap them. So now I'm going to swap them. Let me make this smaller so that those of you that are trying to write can still see. Okay, so this becomes 2, 3, 1. Now I say, okay, what's the first place that I see a number that comes after that number plus 1? That's going to be 1. And I swap it with that number plus 1. So now I look at this one, and these swap. So this becomes 1, 3, 2. And then I do the same question. I say, what's the first place that I see a number that occurs after that number plus 1? That's going to be 2. and then I swap them. And then this becomes 1, 2, 3, and then we finish. Then our algorithm is done. Because the condition only kicked in. We only did something if they were not all in order. So the idea is if I have something which is out of order, then I can try to put it in order by making a bunch of swaps, right? And what I'm going to do is I'm going to look at the first place that I see something where a number plus 1 occurs before the number, and then I swap them, and I just do this iteratively until I get them in the right order. Okay, so what's the point? The point is if I eventually I get that J0L equals 0 and J0L n minus 1 equals n minus 1. So if I do it enough, I'll eventually get in the right order, agreeing with I0. And let's recall our setup, right? So if we scroll back here, we knew that if I looked at these guys and recall that this is the same as phi A0 through A n minus 1, these were true on phi, and these guys were false. So I have something which is false, and it's out of order, and I do a swap, and then maybe it's still false, and then I do another false. Then I do another swap. Maybe it's still false. Then I do another swap. Maybe it's still false. But eventually, it has to change, because I know that once I have them in order, phi becomes true. That's what I see here. So because after enough of these swaps, I end up with the thing in the right order, I know that there has to be a first swap where the truth value changes. Okay. So there is a greatest L prime such that we have not phi A J0 L star dot A J n minus 1 L star. So far, so good. Now, just for simplicity, write B Q for Q in the rational numbers. It'll be this funny tuple. So we're going to have A J0 L star. This is really bad, I'm sorry. Dot 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 all the way up to let's see. Wait. Yeah, okay, it's fine. So, okay, I'm not going to do this actually. So I was going to write it in a way that's really cumbersome, and then that doesn't correspond to the simplicity that I want. So what we're going to do is we're going to write C of xy will be the following formula. It's going to be phi of A J0 L star dot 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 x dot 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 y dot 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 A. Sorry, I'm running out of space. Let me zoom in a bit. Let's shrink this. and A, J, n minus 1, L star. And these variables, x and y, this one will go, say, in the I L star spot, and this one will go in the I prime L star spot. Okay, so now we've replaced the two things that we swapped with just variables. And what we'll do is for AQ, for Q inside the interval, let's see, what do we want? We want K of L and K of L plus 1. Let me draw a picture because I know I don't want to lose all of you, and I know that this is getting kind of hairy. All right, so let's just take stock before we get into the nitty gritty. So we had our tuple. So here's like 0, 1, 2. Let's worry about the simplest possible case. So let's suppose that we've enumerated J0 in the following way. So let's suppose that J0 is something like J0, J2, J1. So J0 doesn't enumerate 0, 1, 2 out of order, but I know that there's just one swap I have to make, which is that if I have this situation, then when I swap these two, the truth value of phi changes. So like in this picture, we would assume that, say, we have phi A0, A1, A2 is true, and phi A0, A2, A1 is false. And then what we're doing is we're defining psi, xy, to be the formula phi A0, xy. Something like this. So this is like an example of our setup. We just look at the place that we swap to switch the truth value, and then we sort of leave the other tuples around as parameters in our formula. Then what do we have? We note that if we look at Q and Q prime, let me say it this way. For Q and Q prime living inside the set, we have, when they're in the right order, meaning when we've swapped them so that the smaller one comes first, we know that phi became true. So we have psi of AQ prime. And here we have not psi AQ prime AQ. And if this isn't clear, let's think back to our example. Well, if we look at these two things, we know that when they're in the right order, then you have something which is true. And now that's just for these two elements, but we're working with an indiscernible sequence. So if I take any two things which are sitting in the right order relations with respect to, say, A0, then it also is true. So if I replace A1 and A2 with any two things living out here, it's also going to be true. So because these tuples live inside this interval between KL and KL plus 1, we know that I'm not going to jump over any of the other tuples. So the behavior of AIL and IL A sub I, or sorry, it's really confusing. So it's like J sub I of L, L star, you know, like the notation is really bad. So anyway, we know that we have this swap. And if we take any numbers inside the interval of the two numbers that we swap, by indiscernibility, when they're in the right order, we get that phi is true, and when they're in the wrong order, we get that phi is false. That's the point. So yeah.
So we want to say that psi of AQ prime is true when
yes,
Q is
yes, thank you. Yeah, when Q is less than Q prime. Exactly, thank you. Very good. Okay, and that means that C has the order property. Taking AQ and I mean, you can define BQ and CQ. As in the definition to just be AQ. And okay, you might worry like, okay, in the definition of the order property, you said that it's less than or equal, but that doesn't matter. You can get rid of, you can replace the less than or equal with strict and it's fine. Cool, okay, so that's it. Now, the next thing I was going to do was to talk about this dichotomy theorem of Shelah, which says that if you have the order property, then either have the strict order property or the independence property. Obviously, that's not going to happen today, but it'll happen next time. So, and the proof is very similar. So I know that this is a bit grody. The idea is just that, you know, if something's out of order, then you can put it in the right order by a bunch of binary swaps, and one of those binary swaps will switch the truth value, and that gives you the order. That's the fundamental idea, and that fundamental idea will appear again in the other proof. So, you know, if you reflect on this briefly over the weekend, then come back on Monday, the proof will be super clear because we'll see it one more time in a slightly different context. All right, so I will stop recording, stop sharing.